Next, we going to derive the flow equation for the unconfined aquifer. Okay, so therefore this is for unconfined aquifer. We have to introduce the assumption, because on the left hand side show the actual velocity distribution for the flow in the unconfined. So we have to record the do-put assumption. Assume that slope of water table is small and respect to the depth of aquifer, and there is no flow on the vertical direction, so we assume that Vz is 0. So in this case it means Vx it means there's no flow on the vertical Vz, so the flow is on x direction only. So this is assumed velocity distribution here. So in this case and this is the area is h. Okay, so we can estimate the flow passing through at any x. Okay, so we can start from to estimate the flow. We can use this Darcy velocity and time the area. The area is mean. Okay, input v time area to get q, so we can estimate to get the flow from passing through the this unconfined aquifer. And the next step, we can we can cut a small element of the confined aquifer to do the same as the confined aquifer. Because we can cut something like this. Cut this small element is dx. Okay, and in the paper is dy. So we can, from this small element, we can draw the this figure. Okay, this is a dx. Okay, and inside the paper dy we draw in 3 dimensions, and we can imagine that flow is passing through this q from 3 directions. Okay, from this part, the first part is first direction, it can be the second direction on y, and from the top to the bottom can be recharged from the top to the bottom. Okay. So we start from to write equation for okay. The other thing, because of the haze, it change. Okay, because in this flow the water level can be like this. If this level change, so water level will be changed. So we expect that the haze can be changed with the boundary condition. So in this case, not only the velocity Vx but haze can be changed. So outflow from this element can be both the velocity and h can be changed. So we can write in terms of the partial differential form. Okay. Or we can start to again to qx, and this qx can substitute with the ax and bx and ax, and for the ax is equal to h times dy. Okay, and we can estimate the mass on x direction is equal to the qx times rho and dt similar to the confined Kiefer, and we can substitute the q into this equation. Qx is equal to vx and ax is equal to h dy dt. Okay. So this is where this equation comes from. Rho vx h dy dt is for the first direction, is for the second direction from in front to the right front, in from front to behind, and is from the top is from the infiltration. Okay, so for so we finish for V out. For V in, so the mass out is we have to plus the delta Vxh into two direction. Okay, and we make subtraction between m in and m out, and next substitute the Darcy velocity in the equation, and we can get the equation of the first equation, the change of mass. Okay, for the right hand side, to estimate the delta m, in this case we have to use the definition of the storativity and storage coefficient is the volume of water take from the groundwater from aquifer respect to the area. Here the change of volume. With respect to the area. So area is dx over dy. This area is dx dy. Okay, so we can, to get the delta m, so we have to multiply by density. Okay, and make equal between equation 13.4 and 0.5. So we can get this, and some term is e, and we can cancel the term. Okay, and finally this is to cancel the on both sides. Okay, and the next we assume the isotopic equation is k is equal to, we can move k from the right hand side to the right hand side, and the next we put h into before differentiate. Okay, so we got this equation. Okay, for confined Kiefer. Okay, if we convert from to use phi to substitute h square over 2, so we got this confined Kiefer, and compare between the between unconfined and confined, you can see that the equation is look similar. It's a second derivative of phi respect to the x, y, and the difference is phi. For unconfined, phi is h square over 2, but confined phi is equal to h.